Let's move on to some related rate problems now. And for this first problem, I'm dealing with a cube, and the sides of this cube are increasing at a rate of 0.2 centimeters per second. And I need to find out how fast is the surface area of that cube increasing when the sides are 10 centimeters. Okay, so a little bit of information there. So let's go ahead and break this down. So I'm given sides, and the sides are increasing at a rate of 0.2 centimeters per second. So what I would like to do is, whenever you're given a rate here, you want to write a derivative expression for that rate. So since the sides are increasing at a rate of 0.2 centimeters per second, the derivative expression for that would be ds over dt. Anytime you're dealing with a rate, you should have time on the denominator, and that's going to equal to 0.2 centimeters per second. After that, if I continue reading the problem, I want to find out how fast is the surface area. All right, so how fast is the surface area of the cube increasing? So surface area has to do with the variable a, so I need to find dA over dt. All right, so I want to find out how fast is the area of the cube increasing the instant when the sides are 10 centimeters. All right, so that's the given information that's given to me in this problem, and now I want to solve this problem by finding a formula that connects the variables together. So since I'm trying to find dA over dt, this tells me I need to start off by finding the area. I need to find out the area of this cube. And the area of a cube is length times width, so s times s is s squared, and in a cube you have 6 sides: the top, the bottom, the front, the back, and then the body. So the area of a cube is going to be 6 sides times s to the power 2. Alright, so my area of a cube is 6 times s squared. Alright, so since I'm trying to find dA over dt, I need to take the derivative of this expression right here. So the derivative of a with respect to time is going to be dA over dt. And then I need to find the derivative of the right hand side using the power rule. So 2 times 6 is 12. And then I have my s. And then the derivative of s, because I'm using the chain rule now, is going to be ds over dt. And then from there, all you're doing is you're substituting the numbers into your formula. So if I just follow the numbers here, s is going to be equal to 10, and ds over dt is going to equal to 0.2. All right, so in order to finish this problem off, this will be 12 times s, which is 10, and ds over dt is 0.2, and that's going to equal to 24 centimeters squared per second. So remember, when you're checking your units, time is always on the bottom, and in this case, area is centimeters squared, so that matches up with the variable on the numerator there. So that answer does make sense for this particular case. Okay, let's move on to part B now. For part B, let me just kind of erase all this. Okay, so for part B, how fast is the volume increasing at the instant when the sides are 20 centimeters? Okay, so how fast is the volume? So basically, whenever you read the term how fast, that means there's a dt on the denominator, and since you have volume, that's going to be dv on the numerator. So I need to find dv over dt when the sides are 20 centimeters. So when the sides are 20 centimeters. Okay, so for part B, I guess we're dealing with the volume of a cube, and volume of a cube is length times width times height. So let's start off with the volume of a cube. So that's going to be length times width times height, which in this case is going to be s times s times s, which is s to the power 3. All right, so if I want to find dv over dt, I need to find the derivative of I need to take the derivative of volume, which is dv over dt. So I'm taking the derivative with respect to time. And then using the power rule here on the right-hand side, the 3 would come in the front. So 3 s to the power 2. And then by using the chain rule, the derivative of s is ds divided by dt. So I'm taking the derivative with respect to time. Okay, and all we have to do now is just plug in the missing variables. So this is going to be 3. S is going to be 20 there, so that's going to be 20 to the power 2. And ds over dt, this was actually given to us at the start of the problem. This right here, that's going to be ds over dt, which is 0.2. So I just need to plug that into my formula here to finish this off. So this is going to be times by 0.2. And if you go to your calculator, that would give you 240 centimeters. Now remember, you're dealing with volume, so it's centimeters cubed divided by time, which in this case is seconds. So seconds is on the denominator there. So 240 centimeters cubed per second. Okay, let's move on to the second problem now. All right, so for question number 2, the area of a melting spherical snowball decreases at a rate of 2 pi centimeters squared per minute. Okay, so let's take a look at the units here. I have centimeters squared, and that's dealing with area. So what that is telling you is that dA, the area, divided by time, dt, is equal to, now the term decreasing means you're getting smaller, so I need a negative sign here. And the rate I have is 2 pi centimeters squared per minute. All right, so sometimes with these related rate problems, you may have to write out the derivative expression right away, which is dA over dt equals to negative 2 pi centimeters squared per minute. You can always check your variables by taking a look at your units and making sure they line up with the proper numerator and denominator there, which they do in this case. And now I want to find out how fast is the radius changing. So as soon as I see the term fast, that has to do with time, and the radius is going to be dr. So I'm looking for dr divided by dt when the radius is 3 centimeters. So that happens when r equals to 3. All right, so I'm trying to find dr over dt when the radius equals to 3, and I know that my area with respect to time is decreasing at a rate at negative 2 pi centimeters squared per minute. Okay, now that you've after you read the problem and translate all the words into derivative expressions, let's go ahead and solve this problem here. And since we're trying to find the how fast the rate of the radius is changing when the radius is equal to 3, for this sphere, we need to know how the radius is connected to the area here. So if you don't have this formula here, the area of a sphere is area equals to 4 pi r squared. Okay, and then what you're going to do after that is you're going to take the derivative of the left-hand side and the right-hand side with respect to time. So the derivative of area with respect to time is dA divided by dt equals 2. Now if I take the derivative of the right-hand side with respect to time, I can use the power rule to start. So 4 times 2 is going to be 8 pi r. And then the derivative of r using the chain rule is going to be dr by dt. And the idea is you're trying to find dr over dt, so I'm trying to find this expression right there. And in order to solve for that, I just need to plug in all the numerical terms that are given to me in this problem. Starting with dA over dt, that's just equal to negative 2 pi. So this is going to be negative 2 pi equals to 8 pi. And then the radius here is going to be 3. And then times that by dr over dt. So the goal is I want to solve for dr over dt. I can get rid of the pi's here. 8 times 3 is going to be 24. And then I can divide both sides by 24. And that gives me dr by dt. Negative 2 divided by 24, if I simplify that, that's going to be negative 1 over 12. And if I take a look at my units here, I have time there, so this is going to be seconds. And radius is measured in centimeters, so this will be centimeters per second. Okay, so the answer is negative 1 over 12 centimeters per second. So the radius is decreasing at a rate of 1 over 12 centimeters per second. Okay, let's move on to the next one.